Like now, okay. So, Priyanka, the floor is yours.
Shall we wait for another minute or so?
Mhm.
Yeah.
So we will take the questions at the end, right?
Yes.
Is it like that? Yeah.
Yeah.
I miss that direct conversation with people. That is, you know, that's something. Yeah, I miss largely.
Okay. Shall we begin?
Yeah, I think maybe you can start now.
Okay. Welcome everyone, and we hope that you all are doing well. So before I introduce our speaker, first I'd like to cover a few housekeeping topics. So can you move to the next slide, please? Yeah. So the code of conduct for this webinar session will be like, please be polite and respectful to the speaker and all participants. Please type your questions in the text in the chat box first, and the speaker will reply to them during Q&A session. We record all the contents in presentation and messages in the chat box. And with this, I welcome you all to the Yes Science webinar series. Thank you for taking the time to attend today's webinar. Dr. Roxy is a climate scientist at the Indian Institute of Tropical Meteorology, Pune. He did his PhD in ocean and atmospheric dynamics from Hokkaido University, Japan. He is a co-chair of the CLIVER Indian Ocean Region Panel and a lead author of the IPCC Special Reports on Ocean and Cryosphere in a Changing Climate. Dr. Roxy was awarded the Kavli Fellowship by National Academy of Sciences in 2015, and he is a recipient of Young Scientist Award in 2016 by the Indian Meteorological Society for his research on the changes in the monsoon. Today, Dr. Koll will speak on climate change impact. So without any further ado, Roxy, the microphone is all yours.
Thanks a lot, Priyanka, and all at the Yes community and all the attendees for coming to listen to this very important and interesting talk on climate change in the Indian Ocean and its impacts. It's evening here, like 6:30 p.m. and we are back to office in Pune in Indian Institute of Tropical Meteorology, which is on the west coast of India. Some of you might know. And we have a Center for Climate Change Research where about 30 scientists work. In IITM, totally about 150 scientists work, mostly on tropical meteorology or oceanography. Yeah. And so today we are going to talk about Indian Ocean, how it is changing and how it is impacting the climate and weather across the globe. Let me see if I can use, yeah. Yeah, you guys can see my laser pointer, right? Good. So this is a very ancient map of Indian Ocean, but there are some features of the Indian Ocean which are quite particular, that you can see from here. So on the west or on the left, you can see the Atlantic Ocean. It is connected to the Southern Ocean and to both the poles on the north and on the south. And similarly, the Pacific also is connected to the north and the south. But the Indian Ocean is landlocked on the north, right? And that makes the characteristics of the Indian Ocean and the climate around this region very particularly different. One particular characteristic is the monsoon. So what happens is that during the summer, during northern summer, the entire subcontinent warms up due to increased solar insolation, and that drives the monsoon winds from the Indian Ocean towards the land. And that this monsoon winds changes the entire circulation and characteristics of the Indian Ocean. Now, let me get you into some other particulars of the Indian Ocean. One is the through flow. You see these openings through the strait. These are the only opening in the tropical ocean connecting the entire tropics, this Indonesian through flow from the Pacific to the Indian Ocean. Now, the climate around the Indian Ocean is changing, especially during the past several decades. Let's get into that. Now, why is it changing? Most of you already know about climate change, global warming, carbon emissions. So I'm not getting into all that. But one of the important impacts from all this is that the ocean is the largest gainer of heat. Ocean is that Earth system component which has gained a lot of heat among all the Earth system components. So on the left, you can see a popular figure from IPCC, the Intergovernmental Panel on Climate Change, which shows the contribution of this additional heat absorbed. Yeah. And if you see the blues, this represents the upper ocean and the deep ocean. And then the ice, the land, and the atmosphere. So the entire ocean contributes or has gained more than 93% of the heat, additional heat from global warming. So the distribution of heat among these Earth system components is quite uneven. There is an uneven distribution of heat among the Earth system components. The ice, land, and atmosphere altogether has gained only less than 7% of the heat. So the ocean is absorbing a lot of heat. Now, among the oceans also, among the ocean basins also, there is a lot of uneven or non-uniform absorption of this heat. You might have heard about or read these lines from George Orwell in Animal Farm. All animals are equal, but some animals are more equal. So similarly, all ocean basins are warming, but some are warming more than the other. And this is a figure from Cheng et al., published in Scientific Reports in 2015, where they showed how the ocean basins are warming over time. So in the recent decades, so all ocean basins are warming at an unprecedented rate, but in the recent decades, you can see the Indian Ocean warming is much larger compared to the other basins. And this is not just for the surface, but also for the deeper ocean also. From 0 to 700 meters, the subsurface ocean is all warming at a very large pace. Now, if you look at the much deeper ocean also, we can see that this warming is reflected over there also for the Indian Ocean. And that is huge. This is for 700 to 2000 meter deep ocean also, which means that there is a lot of heat being absorbed by the ocean, particularly the Indian Ocean. And this might have repercussions for the global and local climate as well. This is a spatial image on how the temperatures are distributed across the tropics. The first figure here shows the sea surface temperatures during June to September for the period 1900 to 1980. And on the right side, you can see the color bars. It goes from 10 to 30 degrees Celsius. Yeah. And the brown color shows the temperatures which are conducive for active convection. So about 26.5 degrees Celsius, you can have active convection. And about 28 degrees Celsius, the convection increases exponentially. And these sea surface temperatures, which are about 28 degrees Celsius, these deep brown colors that you see here, that region is called the warm pool region. This is the Indo-Pacific warm pool, mostly contained by the West Pacific and also the Indian Ocean. And these are permanently warm temperatures over the Indo-Pacific region that supports intense rainfall and also supports the circulation, the global circulation, the water circulation, and also the trade winds. Yeah, and you can see that based on the north-south migration of the solar radiation, the location of the warm pool changes. So during summer, it's more on the north. During winter, spring, it is more towards the equator. So this is quite important because the location of the warm pool also determines how the weather and climate are. Now, the point here is that if we compare the earlier period to the recent period, that is 1981 to 2080, that is in the last 40 years, the warm pool characteristics have changed. The warm pool has expanded in size, and not only that, the intensity has increased. So look at the temperatures where it was 30 degrees Celsius. It was only in parts of the West Pacific, right, in summer. But if you look at the recent 40 years, you can see there are temperatures above, mean temperatures above 30 degrees Celsius in a larger area. So the warm pool has expanded over time. And this is true for both the seasons, if you compare the earlier period and the later period. Now, what has caused this warm pool expansion? Now, there are a lot of studies which shows the mechanisms on how the winds redistribute the SST, the sea surface temperatures and the warm waters across the global oceans. And there are other studies looking at the mechanisms in the water circulation. So there are many important studies on how the mechanisms have resulted in a change in the warm pool or the warm pool expansion. But the root cause can be traced back to human-caused or anthropogenic emissions. So this is a study by Weller et al. In Science Advances in 2016. So what they showed is that when they compared the observations and some model experiments, is that if we had only natural forcing, the sea surface temperature anomalies won't have increased that much over the Indo-Pacific region. So the black line here shows the Indo-Pacific region. It doesn't show any increase in temperature at all if there was only natural forcing. But come greenhouse gas forcing, with greenhouse gas forcing, it increases the temperature across the tropics. So that is what they are showing in this time series here. They are showing, so we have a top panel which shows the SST anomalies, the sea surface temperature anomaly, and also the area of the warm pool region. So if you look at that, the blue line shows the natural forcing. That is without any external carbon dioxide or greenhouse gas forcing. Without any greenhouse gas forcing, the blue line shows that there won't be any expansion of the warm pool or increase in the intensity of the warm pool. So this is true for the SST anomalies and also the area. There is no consistent increase in the area of the warm pool, whether it is over the Indo-Pacific or the Indian region, Indian Ocean or the Pacific Ocean. But If you have the greenhouse gas forcing, that is a red color, we can see a consistent increase in the warm pole intensity and also the area. So which means that human caused emissions are a large reason for the warm pole expansion. I'm not getting into much details about how the compensating factors are resulting in the observed expansion of the warm pole. Now, we saw the mean temperatures until now. The change in temperatures are much more evident if you look at the trends or the change during the last several years. So this is a change in, or the change in sea surface temperature during the past how many years? Almost 120 years. The values are in degrees Celsius, the anomalies are in degrees Celsius. So you can see there is large basin-wide warming of up to 1.2 degrees Celsius over the Indian Ocean and the warm pole region. So if you remember the background SSTs, the SSTs were largest over the Indo-Pacific warm pole region. Now the largest trends, long-term trends, are over the Western Indian Ocean and over the Equatorial Indian Ocean region. Now that's the case for summer. Winter also shows similar figure, similar distribution for a long term. Now there are of course decadal variabilities, but all these figures, this is for the recent period, last 40 years. This also shows consistent warming in the Indo-Pacific region with enhanced warming over the Indian Ocean region also. So all these have impacts. This has impacts on the Asian monsoon. We will go through these impacts. There is a weakening of the Asian monsoon. Sea level rise because warm water with increased warm water, you have warm water expansion, which increases the sea level. Changes in ocean circulation, intensification of cyclones, extreme rains and floods, impact on marine ecosystem, and changes in the Madden-Julian oscillation. We'll go through some of these in the next few slides. And these trends are not only on the surface, these trends are observed in the subsurface also. This again a picture from Cheng et al., which shows that the subsurface temperatures are also largest over the Indo-Pacific region, 1 to 100 meter and 100 to 300 meters. So that it's consistent. The change in temperatures are consistent throughout the surface and subsurface and deep ocean. Now, we will go through these impacts of SST warming on a time scale basis. We will go from extreme events at a high frequency and long-term changes from going from high frequency changes to low frequency changes. So let's have a look at the cyclones. Some of you who have been watching the Indian Ocean might have seen that the Indian Ocean was bombarded with back-to-back cyclones recently. One was Cyclone Nisarga on the west coast of Indian subcontinent, and again another cyclone Amphan on the east coast of India. On both the basins, Arabian Sea and the Bay of Bengal. And both were strong cyclones, both intensified quite strongly. The cyclone Amphan was one of the strongest cyclones that Bay of Bengal has seen during this time. It reached up to category 5, which is about 200 to 250 kilometers per hour. Now, the peculiar factor is that the cyclones in the Indian Ocean, especially the Arabian Sea and Bay of Bengal, they are intensifying quite fast. We call it rapid intensification of cyclones. Now, this is a feature we have been observing in the last few years only. And that we find that this is due to extremely high temperatures. So in the case of cyclone Amphan intensified from a category 1, that is about 100 to 150 kilometers per hour, to a category 5 cyclone, that is 200 to 250 kilometers per hour cyclone, in a matter of just 18 hours. That's like like when you went to sleep, it was depression or a very weak cyclone, and when you wake up, it was a super cyclone. Or like if you consider the case of U.S. elections, when you go to sleep, Trump was winning, and when you wake up, Biden was winning, right? So just overnight, these cyclones are changing. And one of the major factors is that the extreme high temperatures in the Indian Ocean that we saw, because the mean temperatures itself are quite high. And when you have anomalies on top of that, that intensify the cyclones. Cyclones generally draw their energy from the convective energy from the warm waters. And I need to show you these two figures on the bottom, which shows the sea surface temperatures during the cyclone. So on the left bottom, you can see the ocean temperatures normally during this time. The temperatures, the color scales are given on the right. You can see the temperatures are from around 29 to 31 degrees Celsius. But during these two cyclones, both in the Arabian Sea and Bay of Bengal, the temperatures were blew all the records. They recorded up to 32, 33 degrees Celsius. And these can be considered as marine heat waves. Now, this is a new term that we have devised in the IPCC. We have been frequently using in the recent IPCC reports and are like part of the 90 or 95 percentile, top 95 percentile extreme heat events in the ocean. So they are like heat waves over the ocean, like heat waves over the land, but over the ocean. And these are riding on a global warming background, supercharging these cyclones. So that is one of the major impacts of a warming ocean on the cyclones. And this is some analysis which is under preparation, which shows that the SSTs before cyclone in the Arabian Sea has warmed quite a lot. You can see the temperatures, these are the mean temperatures before the cyclone, from 29.5 degrees Celsius to about 30.5, 31 degrees Celsius during the pre-monsoon period. So, and the number of cyclones in the recent period also have increased compared to the earlier period, especially in the Arabian Sea. Now, one of the reasons could be that the warm pool has expanded. This is an important picture that you have to keep in mind. This shows the mean temperatures in the Indian Ocean. We have the warm pool here, and we have the Western Indian Ocean region here. Now, the Western Indian Ocean region is below 28 degrees Celsius. It's not that conducive for active convection. But with warm pool expansion or increased temperatures over here, this region is also becoming fertile. So that is an important point for the Arabian Sea or the Western Indian Ocean region. We can see a lot of storms developed over this region recently. We will get into that soon. Now, I talked about marine heat waves in the Indian Ocean, right? So the same marine heat waves which intensified Cyclone Amphan also resulted in coral bleaching in the same region. In this region, we have a coral reef location called Gulf of Mannar. You can see the corals over that region. So what happened in late May, April, May, because of very high temperatures of 30 to 33 degrees Celsius, most of this coral had severe bleaching. Now, what causes this bleaching? Corals have a mucous membrane. It's called zooxanthellae, which acts as their shield and gives the color. And the warm temperatures strips them away of this zooxanthellae. And that's what results in coral bleaching. And with the bleaching happening many times, the corals get killed. Now, why are we bothered about corals? Corals are only 0.1% of the global oceans, but 25% of the marine biodiversity is located around the corals. And these back-to-back marine heat waves are resulting in more and more coral bleaching in the recent years. And IPCC in the recent report, this is a report you should go through, special report on oceans and cryosphere in a changing climate, which was published last year. They showed that the marine heat waves are increasing globally. On the left, top left, we have a picture of the marine heat waves during 2015 and 16, and denoted by degree heating waves. weeks, this is a cumulative heating which occurred. So you can see that over the entire globe, there are a lot of marine heat waves occurring in the recent years, and the dots shows the bleaching. Now, one question you might ask is the largest warming is, or the marine heat waves are over this region, right? But why no coral bleaching over there? But the coral bleaching is mostly over the Indo-Pacific region. You can see the Indian Ocean, a lot of coral bleaching, the East Indian Ocean and the West Pacific, a lot of coral bleaching. Why is that? One reason is that most of the corals, so if you look at the right picture on the right, most of the corals are in the Indo-Pacific region. So I said corals occupy only 0.1% of the global oceans, and that 0.1% is largely in the Indo-Pacific. So it's quite important to monitor these marine heat waves. And what the climate projections say is that if we had marine heat waves like 1 in every 100 days in the pre-industrial conditions, that's going to increase with 1.5 degrees Celsius. It is going to be 1 every 6 days. And if the temperatures are going to rise by 3.5 degrees Celsius, it's going to be 1 every 2 days. Now, this can be anywhere over the globe. And I'm not getting into detail about this picture, but it shows a steady rise of marine heat, the probability of marine heat waves with global warming temperatures. So, which is an interesting situation. Now, one of the factors that comes up with this ocean warming, whether it's Indian Ocean or global ocean warming, is that it results in compound events as well. On top of, I show the impact of impact on the corals before and after a cyclone. So before cyclone, you can see the corals are well structured and colorful, but after the corals, because of the cyclone winds and the storm surges, the corals are broken and they have bleached. And similar thing happens due to a marine heat wave as well. Before and after a marine heat wave, it goes through a bleaching. Now, in the earlier picture, you saw that in the Indian Ocean, we had marine heat waves triggering a cyclone, which can kill the corals. And at the same time, the same marine heat waves will bleach the corals as well. So damage due to cyclones and bleaching due to marine heat waves. And when these multiple events overlap, we call them compound events or overlapping events. So these kind of events are also happening in the Indian Ocean. At the same time, there are also impacts in the marine productivity. You might have heard about marine phytoplankton. The Indian Ocean is the region with one of the largest upwelling due to the monsoon winds. And that upwells a lot of nutrients and results in a lot of phytoplankton, especially in the Western Indian Ocean and the Arabian Sea region. Now, if we look at the trends in the chlorophyll, which represent the marine productivity, there is a decreasing trend. These purple colors show a decreasing trend. And this is matched in a normal case, there is a mixing between subsurface and the surface, right? And this mixing brings in a lot of nutrients. Nutrients are generally located in the subsurface. And this brings in a lot of nutrients to the surface, which act as food for the, or fertilizer for the microscopic plants or the phytoplankton. Now with warm waters on the surface, warm waters on the surface makes it stratified. So less dense waters on the surface and denser waters on the subsurface. That prevents mixing of subsurface waters with the surface. So this stratification limits this mixing of nutrients, okay, to the surface. And that prevents phytoplankton productions on the surface. We can see increase in sea surface temperatures over the Arabian Sea and a consequent decrease in chlorophyll over that region. There are some studies focusing on that. So that is one impact on the marine productivity. And that can reflect in the marine ecosystem like fisheries. This is a timeline of fisheries over the Indian Ocean, particularly tuna. Tuna is the most caught fish in the Indian Ocean. There is even an Indian Ocean Tuna Commission. And most of the tuna is exported from the Indian Ocean. And we can see that tuna numbers have declined over time. Now, this is not because of climate change, but largely due to large-scale industrial fishing. But the point is that the increased stresses due to increased temperature and the phytoplankton decline can be added stressor to the marine fisheries as well. And similarly, there are some studies from the Central Marine Fisheries Research Institute in India, which shows that sardine catch rates are also projected to decline in the future. From by 2020, 2030, the sardine catches will be around 20 or 30% less than earlier estimates. And this might go up to 60% in the future by the end of the century. So that is a worry because it affects the food and food security of the Indian Ocean rim countries and also beyond. Now, coming from the ocean back to the land, there are some other interesting impacts also to be that we should monitor and to be concerned about. Some of you might have heard about the locust swarms, which swarmed Africa, parts of Africa, Arabian Peninsula, and the Indo-Pac region. Locusts are like grasshoppers. They are solitary creatures, but when the times are conducive, they grow in a swarm, they breed in a swarm, and go across the entire region, surviving on the vegetation, damaging all the crops all around the region. So what happened in East Africa in the recent years? So what happened was that in 2018-19, late 2018 and 19, a lot of locusts bred over here and spread over to the Indo-Pac region through Arabian Peninsula. So if you look at the weather history behind it, we can see that again we are coming back to the Western Indian Ocean region. Yeah, so generally this is not conducive for active convection. But look at this figure on the right. You can see the Western Indian Ocean temperatures in the red, right? Compared to the rest of the temperatures. So the temperatures of the warm pool are shown here. It also has gone up, but the average temperatures of the Western Indian Ocean has gone up at a much more rapid pace. It has almost reached the warm pool temperatures, closed in the gap, early gap in the 1900s, right? And it has reached the warm pool temperatures, which is quite large, which means it can support, Western Indian Ocean can support a lot of convection now. And this has triggered a lot of storms in the last 2-3 years, which resulted in a lot of rains. So storms and cyclones happened in the Western Indian Ocean region, released a lot of rains in the desert area in the East Africa, which triggered a lot of swarms of locusts. And these locusts moved across with the favorable winds and the moisture to the Indo-Pac region, where also they found favorable vegetation and rains. So that is kind of one very important impact of Indian Ocean warming, which goes through many disciplines. I've shown this bird picture because this is from north part of India. This is a bee eater, and it's holding a locust. So this locust is not the usual food for this bee eater. It usually its diet is usually consists of other insects and caterpillars, but not this locust. So this has changed the biodiversity also over this region. Now, coming back to a much more larger phenomena, I talked about the South Asian monsoon, how the South Asian monsoon forms because of the differential heating between the ocean and the land, right? So generally, during summer, the Indian Ocean is relatively cooler than the land. The land warms a lot, and relatively the Indian Ocean is cooler, but it's still a warm pool and supports active convection. And this drives a lot of warm, moist air towards the land, right? which falls as the monsoon rains. Now, if you look at the global temperatures, land temperatures are supposed to increase much faster compared to the ocean temperatures. You have the land temperatures in red here, global ocean temperatures in the blue here, which means that this land ocean temperature gradient should increase, ideally increase. Here also on the right, we have the global distribution of temperatures. We can see the northern hemisphere as largely warmed compared to the ocean. But if you look closely over the Indian Ocean region, we can see that there are some more red colors in the ocean than over the land. So we will get into that, right? But generally, if land was to warm much more than the ocean, the monsoon should have increased. Because generally with increased sea surface temperatures, the convection should also increase exponentially. But if you look at the long-term series of the monsoon, we can see that there is a decline in the monsoon. So these numbers or the rainfall averages are from the Indian Met Department from 1870s to 2020, over more than 150 years. And it shows there is a clear interannual variability in the monsoon rainfall over India. There is a decadal variability of monsoon over India. But if you compare the recent period, we can see there are more red colors, right? Now, what does the red and blue mean? The blue means wet years or flood years, we call them. And the red means drought years, less than 10% and greater than 10%. And the gray means within the normal. And if you look at the earlier period, 1870s to 1950, we can see the blues and the reds are intermittent. There are periods with wet rainfall and drought periods as well. But if you look at the last several decades, we can see the number of droughts have increased tremendously. And especially since 2000, there hasn't been any strong wet years at all. And the slump, I have drawn this multi-decadal variability. You can see that there is a slump in the rainfall over here. And we have to think that this is not regional rainfall. This is all India rainfall over a large region. So if this slump means a lot in terms of the rainfall changes. Now, why is that? One of the reasons that we have understood is that there are multiple reasons for that, including aerosol, carbon emissions and all that. But one major reason is the change in the land sea temperature gradient. Now, this is a zoomed in picture of the land and ocean temperatures during summer. We can see there is a large sea surface high sea surface temperatures or of up to 1.2 degrees Celsius over the ocean. But over the land, though the other regions have the temperatures have increased tremendously, over the land over India, the temperature increase is not that much. And this is reflected in the upper atmosphere also. These are the upper atmosphere temperature trends. Over the ocean, of course, we know increased sea surface temperature, it supports increased convection. So there is increase in temperature over the ocean also. So this land ocean temperature difference has weakened the Hadley circulation. This is on the bottom panel, you can see the vertical wind velocity. So there is enhanced convection over the ocean, equatorial ocean, and to compensate that, there is a compensating subsidence. So this subsidence over the land dries and decreases the rainfall over the Indian rainfall over the Indian region, reducing the rainfall. Now, if you take short time periods, we can see that these patterns keep changing. There has been a recent study by Jin and Wong in Nature Geoscience, which says that although the long-term trends show a larger warming over the ocean and lesser warming over the land temperatures are now catching up, which is interesting. So between 2000 and 2020, the land temperatures are also warmed. So it looks like it is a tug of war between ocean and land temperatures, which is warming faster. So accordingly, they are shown a temporary increase in rainfall in the Indian monsoon as well. Now, how is it faring now? We checked the temperatures post 2010, And we saw that the temperatures are, the Indian Ocean continues to warm. And CMIP 6, CMIP 5 projections also shows that the temperatures are going to warm monotonously over the Indian Ocean region, which means that we need to keep monitoring this region. Now, the problem is that it is not just droughts, but at the same time, there are floods as well. If we take the entire Indian subcontinent, and this is true for all the Indian Ocean rim countries. So this is an example focused on the Indian subcontinent. The gray line here shows the mean rainfall over a 60-70 year period. So we saw that the mean rainfall is decreasing. But if you look at the extreme rainfall events, the orange line shows the extreme rainfall events. There is a decadal variability, but there is a consistent increase in extreme rainfall events. And these are rainfall events which are defined by above 150 millimeter per day. And there is a threefold increase in these extreme rainfall events at the same time when the mean rainfall is increasing. I'm not going into all the mechanisms behind it. It's explained in this Nature Communications paper, but basically we are having long dry periods intermittent with heavy rainfall events. So very simplistically taken, we can think of it like this. When the atmosphere is more warmer, when the atmosphere is warmer, the water holding capacity or moisture holding capacity of air increases. So it can hold the moisture for a longer time and more moisture. And when it rains all of a sudden and the amount is large. Now the impact of this is huge because a recent study by Richardson et al. Shows that in the rural areas, deaths due to suicide increased by 18.7% during floods compared to 3.6% during droughts. Now that may be because the property damage due to floods might be quite large compared to that during droughts. Priyanka, how many more minutes can I take?
So you can, like, if you can finish within 3 minutes or so, because then we can take questions.
True. Okay, so now I am getting into other changes also on it, which are happening over a long time. I might skip some slides because I thought it was important to explain some of these events and mechanisms. Now, the important factor with the warming Indian Ocean is that it changes the sea level across the Indian Ocean. And from this image, you can see that the most vulnerable nations due to climate change are on the rim of the Indian Ocean. These are low-lying land where the population is high and where people don't have early warning systems or adaptive measures. And this includes Africa, South Asia, and also East Asia. And this figure shows the trend in sea level rise across Indian Ocean. You can see it's non-uniform. The reason why it's non-uniform, because the warming also is non-uniform. That is one of the reasons. And also the distribution of the warm water across the basin is different, which result in a non-uniform sea level rise. So some regions, the sea level rise is up to 5 millimeter per year. That's about 5 centimeter per decade. So if you take a century, that's like 50 centimeters, half a meter sea level rise along the cities like Dhaka, Kolkata, and maybe 30 centimeters along the Mumbai coast. So that is a huge increase in sea level, right? And some of the visible impacts of sea level rise are already happening in the Indian Ocean. This is an island which is almost disappearing. It's again in the Gulf of Mannar where the marine heat waves are active. So it's almost getting disappeared. And this small innocent creature here, that is the first species to be extinct due to anthropogenic climate change. This happened in the fringes of the East Indian Ocean, where some of the islands where these animals were endemic disappeared altogether due to inundation, flood and inundation. Now, there are ways to work against this by seagrass restoration, and coral reef restoration, which brings back some of this biodiversity, right? So there are positive stories as well. Now, I will quickly go through, I have shown the major impacts of Indian Ocean warming or the Indo-Pacific warming on the climate, especially over the Indian Ocean rim regions. There are far-reaching impacts also. I will show you in just three slides here. One is through impacting the eastern US fall precipitation through wave trains, atmospheric wave trains emanating from this region due to Indian Ocean warming affects the precipitation over the eastern US. That's during fall. So that is one of the impacts of Indian Ocean warming. Another important study which came recently was its impact on the Atlantic meridional overturning circulation, which means it can impact the very long-term climate change of through the ocean circulation. What they showed was Indian Ocean warming of 0.1 degrees Celsius can intensify the AMOC or the meridional overturning circulation by one Sverdrup. One Sverdrup is about 1 million meter cube per second. That's huge amount of water being transported, right? So the impacts are huge. Another study showed that the Indo-Pacific warming impacts the global rainfall patterns by changing the circulation. Because of warm pool expansion, it changes the circulation totally and changes the Madden-Julian oscillation, which propagates from the Indian Ocean to the Pacific. I'm not going into all these details, but it shows that the impacts of Indian Ocean warming are not only in the Indian region, but it is far-reaching. It reaches the extratropics in the US, in the South American region, in Australia, in Africa. So we need to keep monitoring it, which comes to my most important and the last slide here. We need to keep monitoring the Indian Ocean. So if you look back to 1990s, the Pacific had a lot of observation systems. Atlantic had some observation system also, but the Indian Ocean was empty. So some of the pioneers in Indian Ocean observation, they came up with the Indian Ocean observing system. We call it INDOS, right? And which has been measuring the changing temperatures and changing conditions over the Indian Ocean. And these ocean conditions go into the weather forecasting system, which provides a forecast for this region and also for ENSO forecast as well. Now, there are many gaps in this, which is why we have proposed a new Indian Ocean observing system. Gaps like over the Somali region due to piracy and all, we are not being able to observe, but this is a very key region. And there are gaps in the Indonesian through flow, which is again a key region for the transport of heat from the Pacific to the Indian Ocean. So we need to improve these observations, but how? This has been detailed in a very important, very detailed panel report from the Indian Ocean panel. This will come out in BAMS in the next few weeks. You can go through that Indian Ocean review, which is in very detail. Now, thanks to all for listening to this talk on the Indian Ocean. These are my collaborators from the Climate Research Lab team. It's quite important to collaborate. I know that the ES team also focus on collaborating. I heard from Priyanka. We have networks like this for the Indian Ocean, where we collaborate with people working on Indian Ocean from different different regions. Then collaboration with IPCC team, and there's a UN Decade of Ocean, which you might be aware of. Thanks to all, thanks to collaborators, and thanks to the audience for listening to this talk. Yeah, we can go back to
Dr. Koll. Yeah, for such an interesting and informative talk. Yeah, so we'll not take the questions. We can already see that we have a lot of questions. So the first question is from Dr. Das. Wonderful talk and excellent initiative. What are the major causes of Bay of Bengal and Indian Ocean extreme warming?
Yeah, so there are several reasons which we have found. One of the reasons is due to how the Indian Ocean responds to teleconnections during ENSO events, like the El Nino events and the La Nina events. El Nino warms the Indian Ocean, but it is asymmetrical when we compare to La Nina. During La Nina times, the Indian Ocean doesn't cool that much. That is one of the reasons. So this is the reason through the atmospheric bridge, through the Walker circulation. But at the same time, there is an oceanic bridge also through the Indonesian through flow that we saw. There is warm water coming in from the Pacific and being stored in the Indian Ocean. And then again, in the Indian Ocean, there is a redistribution of this heat due to internal ocean dynamics and also the winds. So these are one reason for the regional distribution of warm temperatures in the Indian Ocean. Yeah.
Okay, so the next question is from Mohammed Abid. 2015-2016 was El Nino year. Does this observed in any normal years?
So I didn't understand that question,
Yeah.
but 2015-16 was El Nino year, and it had an impact on the Indian region also. The Indian Ocean was abnormally warm, and it had impacts on the monsoon as well. Yeah. I think, yeah.
So the next question is from Parvati. Hi, Roxy. Thanks for a nice talk. I have a question on the marine heat wave, which you showed in the initial slide. Ideally, we expect the cyclone to mix the ocean and hence causing a reduction in the SST. But in the particular case of Amphan, on other hand, we saw an increase in the SST even after the cyclone started. I'm just curious to know how marine heat wave can sustain even during such a strong wind system that can churn the ocean.
Yeah, so generally, so the temperatures that I showed in my slide was the temperatures before the cyclone, but Parvati is talking about the temperatures after the cyclone. So obviously, we expect that the temperatures will cool down phenomenally after the cyclone because it churns out mixing due to the winds and cool the SSTs. But one thing we have seen, one of my student Vineet Kumar Singh is studying cyclones and their interaction with the ocean. So depending on the translation speed of the cyclone, that is the movement of the cyclone, that also determines the cooling below. So if a cyclone is moving quite fast, the temperatures below may not get a chance to cool down that much because the coupling between the cyclone and the ocean below, the coupling from cyclone to the ocean may not be that strong. So it moves quite fast. So that could be one of the reasons. So this being still explored, and that's one thing. So we are coming out with a review of ocean cyclone interactions. Hopefully we will give more, we will talk more about it then, but this is one of the things, yeah.
Okay, next question. In the slide where you showed the trend in subsurface ocean in recent decades, a region of cooling is visible at the west central tropical Indian Ocean. Can you please explain what may have caused it?
Yeah, so in the subsurface ocean, there are gyres in the Indian Ocean as well. So this cooling in some region in the Indian Ocean, and this is reflected in the sea level also. The sea level over that region has not increased that much in the recent years in the Indian Ocean, and the reasons are traced back to ocean dynamics and redistribution of the waters due to the ocean circulation. That's very simplistic response to that. I'm not getting into the details now.
Okay, next question is from Elizabeth George. Shouldn't the sea temperature increase as well when there is an increase over the land? If global warming is what is causing it?
Shouldn't the sea increase as well when there is an increase over the land? So I'm not sure if I understood it fully, but of course we expect that both land and ocean warms consistently with increasing global emissions. But the thing is that there are multiple factors, atmospheric circulation. For example, there are factors like atmospheric pollution, or we call it aerosols. Now, in South Asia, aerosols are an important factor in terms of controlling the solar radiation. So aerosols can absorb or reflect solar radiation. So based on that, the temperatures over the land would be different from that of the ocean, where the aerosols are comparatively or relatively lesser. So that could be one reason with, differential heating of the land and ocean.
Next question is, congratulations, Dr. Roxy, for your superb presentation. I would like to know why Bay of Bengal region sea level rise show more rising trend compared to the Arabian Ocean region.
So this I'm not sure if I have the answer for you. That may be a research problem which can be explored. One of the reasons could be that there is maybe the winds are redistributing more warm water to the northern Bay of Bengal, but I'm not sure. But remember that if you look at the background sea surface temperatures, Bay of Bengal is much more warmer than the Arabian Sea. So even if we have the same anomalies of anomalous temperatures of the Bay or the Bay of Bengal and the Arabian Sea, maybe Bay of Bengal responds much more in a larger way compared to Arabian Sea. I'm not sure. That is something that's a research problem which should be explored.
Next question is, I would like to know why Indian Ocean region is warming rapidly rather than Pacific or Atlantic.
So again, I think I responded to that briefly earlier. So through the atmospheric circulation, we have a asymmetric response to El Ninos and La Ninas. There is more heat coming to the Indian Ocean, but again, Indian Ocean is a landlocked region, and there is less heat escape. The flushing rate from the Indian Ocean is much less compared to the other oceans. Also, there is more heat in the recent years coming from the Pacific to the Indian Ocean. Atlantic is also warming at a very large pace. But it also depends on where the heat is stored. Pacific Ocean is quite large and the winds blow throughout, but the Indian Ocean is small and confined. So there could be multiple reasons on why it is particularly on the Indian Ocean and the Atlantic.
Question is from Carolyn. Thank you for a brilliant presentation. In how far do we see a visible impact of El Nino or ENSO patterns in the Indian Ocean? What impact do we have on ocean circulation and eddy formation?
Yeah, thanks, Caroline. I hope that I can partially answer that. So generally, when we have a El Nino in the Pacific, it modifies the water circulation and the winds get weaker over the Indian Ocean. And when we have weaker winds over the Indian Ocean, there is less evaporation, so the temperatures are warm. Now, these warm temperatures persist for a longer time. Even if the El Nino weakens, these warmer temperatures over the Indian Ocean, because it doesn't get flushed out fast and the winds are weak, it persists for a longer time. And also, there is a feedback with the monsoon. So the winds are weak, the monsoon winds are weak, it strengthens the SSTs, and the SSTs are warm, it weakens the monsoon winds further because of the land sea temperature gradient. So that acts like a vicious circle which keeps the SSTs persistent over the Indian Ocean for a longer time. Now, that can impact the ocean circulation also, the monsoon circulation over that region. But we have no clear understanding of that, but there are some studies which shows that the cross equatorial circulation has changed and all. I think one of my colleagues, Swapna Panikal, she's working on the ocean circulation. So there are some early results on how the ocean circulation is also changing. Obviously, the Indonesian through flow is changing. There are some studies showing that the agulas might be changing. It might be thinning or widening. There are debates on that. But one research problem is that we don't know how the Somali currents are changing. The Somali upwelling system with the Somali currents are one of the strongest currents. These are the reversing currents, but we don't know how it is changing. That is an interesting research problem for youngsters like who are in the audience. Yeah.
Okay, next is amazing talk. I would like to ask the effects of Arabian Sea warming on the oxygen minimum zone, since primary productivity is projected to decrease.
Yeah, so if we just have a look at the INDOS2 report, the Indian Ocean Observing System report, there we have a chapter focusing on the oxygen minimum zones. So clearly what happens is that because of stratification, so we have ocean warming, it stratifies the surface waters. There is less mixing happening of the subsurface waters with the surface, which decreases the oxygen content or the dissolved oxygen in the ocean, which affects the primary productivity, which affects the marine ecosystem also. So obviously there is a expansion of the oxygen minimum zones, which is happening both in the Arabian Sea and the Bay of Bengal, which are, regions of large oxygen minimum zones.
How will the global ocean circulation affect this marine heat wave?
We don't have much idea about that, but we are seeing that at least part of the global ocean circulation, like the Lewin current in the southeast of Indian Ocean along the coast of Australia, this along with the ITF, it also transports a lot of warm water. So these are warm waters coming from near equatorial regions to the south of Indian Ocean, where it is generally cooler. So these are resulting in marine heat waves over there also. So these are important phenomena which are coming up in the recent years, which we are still monitoring. Yeah.
Next is thanks for a great talk. It is quite exciting to see the progress in Indos. Are the existing data made available to the public?
So so Indos, when we were reviewing the Indos, or when we were considering Indos or the Indian Ocean Observing System, one major factor was that we will only consider observation systems which have an open data policy. So all the data in the Indos are available in public domain. So some of the networks are like Rama research. I forgot it's research. I forgot the full term. These are moorings in the Indian Ocean, and Argo buoys. So all these data is available freely to the public, and we are also pushing governments to make their networks available in the Indos. Like India has some moorings in the Indian Ocean. They are called Omni moorings, which are in the northern Indian Ocean. The data was not public until now, but we are now bringing that along with the Indos. They are now called Rama Omni moorings. So this is a step forward which we are making. Now there are some more efforts to be done. It's only in the Indian Ocean we have these exclusive economic zones where the data is not at all available for the public. And that is some barrier that we have to break in the future, so that because coastal dynamics is quite important for climate system. Yeah, whether we consider Somalia pulling or other regions. So all the data is available, and the report is available online as well. Just search for Indos 2.
Great. So yes, we still have many interesting questions, but unfortunately we are out of time. We'll try to answer your questions. Like, Roxy, will that be okay if we can communicate through emails?
Yeah, perfect. So
yeah, because everyone is registered, we have the email address, and we can answer the questions through email.
Yeah, so just shoot an email in this email ID I have put in the chat. So and I'm always available for all young scientists for any scientific questions, or even questions about your career or anything like that. I'll be happy to discuss with you all, guys.
Yes, and if you have any other question remaining, you can type your question here, and we'll send him a list of questions, and the answers will be sent to you via email.
Yeah, perfect. Yeah.
Okay. Thank you, Dr. Roxy, again for your time, to share your research with the YES community. And for everyone, the recording will be available tomorrow on YES Community YouTube channel. And so this concludes our 2020 science webinar series, and we will be back next year with many such interesting topics. And the information will be shared on our website and social media platforms. So to know more about the next series that we'll be planning and other yes activities, you can follow us on Twitter, Facebook, or LinkedIn. And thank you everyone again for your time. We're sorry that we cannot take all your questions, but we'll try to answer your questions.
Thanks to all for a wonderful discussion, stimulating discussion, a lot of interesting questions. I enjoyed that. I enjoyed talking to you about Indian Ocean, and I'm happy that I'm able to bring forward the enormous importance of Indian Ocean, such a small ocean, but the warming is so huge and the impacts are far reaching. And we have all the Indian Ocean rim countries, which are quite affected by the changes over this region. Thanks to all, thanks to Priyanka, thanks to Valentina, thanks to Yes community, all the technical support. Thanks to all.
Thank you. Bye.
Thank you all, and bye-bye. See you next time.
Bye.